Share the screen. Check to see if it's using the right audio. And I think it is. All right, good. So hopefully people can join the meeting. And what I'm going to do is I'm going to open up Twitter and have it in the corner. So if people want to ask questions during class, they should be able to tweet me, and it ought to pop up a little box. So there's a possibility I will see it. Anyway.
You don't want to use the chat app from Zoom?
Chat what?
The chat box in Zoom?
That doesn't seem to work. People can try that too. The things inside Zoom don't pop up, and I have to remember to look for them, and I often forget. But for anybody watching the live stream, and I seem to have 5 already, please tweet me or something. Contact a student. I've had some people in contact with students that are here. Let me know if something's wrong. Last time I was teaching a class, I had no sound for the first 10 minutes, and then I had the wrong video turned on, so all they got was a picture of my face and couldn't see the slides for the next half hour. So if something like that is going on, please let me know. Because one problem with this amateur stuff I'm doing is I have no feedback. I can't see or hear what I'm projecting. So if it's wrong, let me know. And so you can try the chat, but I think your best bet is probably to tweet me, because I think that'll pop up a box and I'm liable to even notice it. Anyway, let me see if I can get some of this nonsense out of the way. I don't know how to get this box to go away or what this thing is. Video. Unmute. Am I mute? I'm not mute. So I think this must be somebody else's video they're sending me. Anyway. All right. So let me put up the schedule. And normally I would talk about news if there was any time. I think I may have used up all the time trying to get this Zoom thing working, but I will probably get less clumsy at it someday. So here's the schedule for this class. All right. So we are at 9/6. So nothing's due yet, because people may still be adding. In fact, did anybody come here to add? All right, maybe that's not going to happen. Anyway, next week, 9/13, I have a guest, which is Tim Ryan. He's a very interesting fellow. He runs the networks here, and he is a bold shaker. I mean, I was the envy of other college teachers when I told them that the network administrator here trusted me enough that he let my students audit the college's security. And I've done that 4 or 5 times now, and it turned out to be a lifesaver, because we hired a crook for a chief technology officer, and he hired a crook for his consultant, who came and claimed that we had 10,000 viruses on the network that we didn't have. And I was the only person in the whole college in a position to state that that was not true, because my students had done audits of the college infrastructure, and I knew it wasn't that bad. And we were eventually able to force him out. Not before he made us the laughing stock of the world by getting newspapers to publish lies about us, but at least we got rid of it. Anyway, so 9/20. Well, there's probably something due on 9. There's stuff due on 9/13, even though I have a guest speaker. I'll be around to help people on that. So chapter 2 quiz due that day, which is the chapter we're going to do today, and project 1 due that day. All right, and then 9/20 is when chapter 3 quiz is due, and project 2 due. All right. So in fact, you got a little more time than I originally planned to do the first couple projects, which really won't hurt anything. Yeah. Right. Right. I'll write it up here. I won't call. Actually, I don't think anybody on the stream might as well have it. Oh, it's going to be the recording now. So to download the VMs, I email it to all of you, but somehow a lot of people don't have it. The username is this, and the password is this. I'll turn on the lights so you can see it, if I can figure out how. All right. That's it. And the only reason I don't just tell the whole world is because some of this stuff is Microsoft proprietary. So I'm not really supposed to be handing out to people that are not students. Anyway, it's also, by the way, on the whiteboard in the hacking lab. There's another place you can find it. But anyway, if anybody has trouble, I'll be in the lab after class. I can help people do it. Any other questions? Well, we're 10 minutes. Yeah.
This is the project one.
Yeah.
No, project two. I'll ask you some phrases.
Okay, fair enough. Yeah. All right. Any others? Well, let's talk about TCP/IP. Hopefully, you have taken a networking class before, Network Plus or something of the sort. So this stuff is not all brand new to you. If it is, we're not going in a lot of depth, but I do assume you have some familiarity with networking. So we're potentially going to summarize Network Plus here. Although we're not going to do the OSI model, which is the big one they use in Network Plus, the OSI model is a 7-layer model, and it was developed in Europe to be a sort of theoretical model of how networking worked. And it's not the way network devices really work. In reality, only the bottom 4 layers are real, and the top 3 layers of the OSI model are always just inside your browser or email client, not separated in a very meaningful way. So here we're going to go with the TCP/IP protocol stack, which has only 4 layers and is actually much closer to the way real hardware is really built. And then a little bit about IP addressing and binary arithmetic. So TCP/IP, let me see if I can possibly get rid of this annoying thing. I've never found any way to get it off the screen entirely. Move to bottom. All right, we'll see if that does any good. All right, anyway. Computers speak protocols so they can talk to other computers, just like we have diplomatic protocols so nations can talk to each other even if they hate each other. And that's, of course, the point of the internet. There are people that do absolutely hate each other, like Apple and Microsoft, that totally don't want to cooperate, and yet they cooperate on the internet. The internet was Unix production, and both Apple and Microsoft came to it very late after it was already out there. All right, so TCP/IP is the protocol stack that runs the internet. And when it was originally announced, it was considered far too confusing and complicated to use for local area networks. At that time, local area networks used protocols like AppleTalk and NetBIOS and so on that were much simpler, where things just had alphabetic names like computer 1, printer 2, and that was their address, no numbers. That was much easier for people to use. But once the internet came out and became useful, so everybody had to be on the internet, then there was no point having 2 protocols, one for your local network and one for the internet. So everybody discarded the earlier protocols and they switched to TCP/IP for everything, with the exception of a few special cases like server farms, which use other protocols like fiber channel for special, and things like storage area networks, but for most end user devices like computers and printers, they use TCP/IP pretty much the same way the internet uses it. So here's the 4 layers. At the bottom is the network layer. This includes the physical network, cables and radio frequencies, and the network card, and the MAC addresses. Your network interface in your computer is a smart device. And what it does when frames come in, it checks to see if the MAC address in the frame matches the MAC address in the card, and it does not send the signal into your computer to go to higher layers unless it matches. And that's its contribution here. It also checks for errors. There's error correction at layer 2. There's a checksum in the Ethernet frame, and if the checksum is bad, it throws away the packet and requests a replay. This is very common on wireless networks. If you go to a coffee house and sniff with Wireshark, you'll often see 10% of the frames in red, indicating they were damaged in transit. Wired networks are quite reliable. Wireless networks are very, very unreliable because there's far too many devices talking on the same channel and they interfere with each other. The internet layer, so network layer takes you to a local area network. This will get you from your computer to a router, or from your computer to another computer in the same room usually. To move any distance across the planet, you use the internet layer. This takes your packets and lifts them out of your local area network and moves them over a large distance to get to the target network. So if you're talking to Google, it takes your packets from San Francisco and moves them to Sunnyvale, where the Google servers are. If you're talking to somebody in China, it takes you there. IP is responsible for finding the physical location of the endpoint. So this is why if you download movies, the Recording Industry Association of America has a record of your IP address, because you had to tell it what physical location to send the movie to so they can find you, supposedly. The problem is an IP address is not really tied to any one person. For example, all the traffic from this college goes out with one IP address, and that's true of most companies. They have internal networks where they use private addresses, and it's all translated to one public address. So if somebody down here was to download an illegal copy of a movie, the person who delivered it would really have no idea which student did it. All they would know is somebody at this college did it. Anyway, the transport layer is TCP and UDP primarily, although there are other transport layer protocols, unfortunately. But TCP and UDP are by far the most common. TCP is used almost all the time because it's reliable. Typically, if you are sending something over the internet, you would like to make sure it really gets there. And TCP makes sure that the recipient is listening. It adjusts the flow rate of data, so it does not send data faster than the recipient can absorb it. And it gets a receipt from every packet, or after every certain number of packets, to say that all data got there correctly. And if any of the packets do not get there correctly, they're resent. So that's TCP, and normally that's what you want. UDP is when you want to just spew out data constantly with complete disregard for whether anybody's listening or not. And that is not something you normally want, but it is used for things like security cameras and live news feeds. And as you may know, if you get a satellite dish, and I think there are some websites that can do it too, you can see raw live news feeds where they're setting up the camera, somebody supposedly coming like the president, you can hear them chatting and waiting for them to show up, and you see the raw picture of what happens, which is then edited and spliced in to make things like TV news. So that's the case in which you use UDP. It's not a very common situation. And the application layer is everything above that intended for the human to see. This is where emails become readable text, videos become viewable videos. So if somebody plays a video on YouTube, they click play and they see a video, and a normal user just knows that somehow that's coming from YouTube, but what we would know is that's actually coming from all these other layers. That video is a whole series of packets flowing to you from Google, and they're passing through all these layers, getting delivered to your machine and reassembled into an orderly stream, which looks like a video. All right, so the application layer is what humans see. So the protocols that directly produce readable text are this way. I'd sort of like to get rid of that thing. Oh, well. Anyway, so HTTP is web pages that you can see. Now most of them are HTTPS. FTP is file transfer, unfortunately. Nobody should be using FTP. They should have all been blocked by the firewall 25 years ago, but a large number of people continue to use it. FTP and Telnet are very commonly used, and they're appalling because they send your password in plain text over the internet, so anybody can steal it. So they're convenient, but they're far too dangerous to use, and everyone should block it at the firewall. If you become a security consultant at a company, one of the first things almost every new security consultant does is try to explain to management why they have to stop using plain text authentication. Almost everyone does it until they finally grow up and actually hire a security professional who is not an idiot. And then it is one of the first things they fix is we should never be sending plain text passwords anywhere. That's just stupid. But people do it, and they don't understand what's wrong with it until they get someone who can explain it to them. Anyway, SMTP sends email. SNMP controls network devices like routers and switches and firewalls. And unfortunately, the most common version of SNMP also sends passwords unencrypted over the network. SSH is the replacement for Telnet, much better than Telnet, so you can send commands to a server and they are encrypted. So you are not just spraying your passwords for everyone, and in fact, all the data that you get is also encrypted so people can't see what you're doing. And IRC was the original chat room, Internet Relay Chat, when many people shared Unix servers, and it is not used for any legitimate purpose anymore to any large extent. There are a very small number of online communities based in IRC that still have friendships and good things going on there, but more than 99% of all the traffic on IRC is malware, botnet command and control, porn, stolen property, and so on. It's been totally taken over by corrupt users, so normal users can rarely find an IRC room that really does them much good to chat in. Anyway, so there's a simple summary of these things. And those are the protocols at the application layer that produce something that a human can read and interact with easily. Below that comes the three layers that are responsible for the network transmissions. And these are not something that the ordinary user is ever aware of at all, but they're stuff that we need to understand as the administrators and technical people. The transport layer is responsible for taking large objects like movies and breaking them up into small chunks. You can only move a small chunk on a network at a time. Unfortunately, The internet is still using the standard from 3 decades ago, and you can only move about 1,500 bytes in one packet, which is incredible. If you watch a video, that video can easily be 500 megabytes. So that video has been broken up into 500,000 packets and sent to you one by one. And each single one of those packets had to hop through about 15 routers to get here on the backbone, and each router had to compare it to a table of 500,000 routes and try to guess which way to send it. It is extremely inefficient, very wasteful, very slow, error-prone, and so wasteful that at last I read the internet backbone consumes 11% of all the electricity on the planet. There are much better ways to do it, but we haven't gone there yet. And one of the many things that would be nice would be to use larger segments than 1.5 kilobytes per packet, which was okay 30 years ago, but now it is ridiculous. Anyway, so the transport layer takes your large object, like an email or a picture or a video, cuts it up into the right size chunks, 1.5 kilobytes approximately, and then encapsulates them as either TCP or UDP segments, which are then sent across the internet by the lower layers. TCP has the handshake. Like I said, TCP is the most common protocol because it makes sure you're getting there. So before you send any data to another computer with TCP, first you send a SYN packet. It replies with a SYN ACK, and you reply with an ACK. Those packets typically do not transmit any data, although the final ACK can transmit data. That's not how it's normally implemented. And the only point of that is to make sure that the recipient is listening. There's no point sending data if the recipient is not listening. And that's what this handshake does. It's the same thing as when you call somebody on the phone and you say hello and they say hello, and you don't bother sending your message until that ritual has happened because you're not sure there's anybody really listening to you. The TCP header is here. This is right from the RFCs. All these things are defined by the Bible of the Internet, which is a series of RFCs, which means request for comment. Engineers write these things, they go over them very carefully with the IEEE and other committees, and then they finally decide on one and it becomes approved, but nothing is in any forever a final state at all. All you ever get is a request for comment. And then there are comments, and then there are revisions and revisions and revisions forever. That's the way the internet is. But this is the original RFC for TCP. This much has never changed. So your TCP packet starts with a series of bytes. These are bits going across the top, 32 bits. So that's 4 bytes across the top. You have 16 bits for source port and 16 bits for destination port. Those are used to sort traffic. So you can have many different kinds of traffic going through the same interface, email and video and whatever else. You have sequence and acknowledgement numbers that are 32 bits each, and those are used to order the packets. So you know they're just numbered, and you line them up in sequence. This is bytes 1,000 through 2,000. Another byte has byte 2,000 to 3,500. Next one has 3,500 to 5,000. And you use the sequence number to line them up. The acknowledgement number is used for data going the other way. Then you have a couple fields here that aren't used much. Here you have the flags. The flags are really important. They specify the purpose of a TCP packet. If you put a 1 here, it's a SYN packet. If you put a 1 in the SYN and the ACK, it's a SYN ACK packet. If you want to cancel a connection, you use a reset. That's what the Great Firewall of China does. If you're in China and you try to go to a forbidden website like Google, you send a SYN, Google sends a SYN ACK, and the Great Firewall, on your behalf, sends a reset. Never mind, they decided not to look at Google. This is what Comcast did. People used BitTorrent for a while. They were caught for it. They tried lying about it for a while, but then people proved that they were absolutely doing it. Then the people tried to get the Federal Trade Commission to outlaw it, and the Federal Communications Commission tried to, and they were determined not to have the legal authority to stop them. So now I think they openly block BitTorrent. But anyway, they would cancel BitTorrent connections to stop people from downloading a lot of content on BitTorrent. Anyway, those are the most commonly used ones here. If you don't cancel a connection with reset and you reach a normal termination, then you end it with fin, which means I'm really done. I've received the web page or whatever you were sending me, and I don't need any more. The window size determines how many bytes of data can be sent before you have to send a receipt, an ACK packet, and this is adjusted for network conditions. If your network is relatively free of errors, the window size gets bigger, so your data moves faster. If you start dropping bits and having to resend packets, then it'll automatically scale the window size smaller and send smaller bits of data before requesting acknowledgement to try to match the most efficient data rate for the conditions of your network. And as I mentioned, wired networks are usually pretty good. Wireless networks are usually pretty terrible. A lot of data being lost. Then you've got a few other things down here that don't really matter much. That's all the TCP header. So that's TCP segment. I say the critical flags are TCP, the critical components. So the flags like SYN and ACK, the initial sequence number is useful for an attack that isn't that important anymore, where you could predict it. And the source and destination port you absolutely need to know. Those are what determines which process on the computer at each end is listening and receiving. So the flags are synchronize, acknowledge, and these other ones like reset and fin. The ISN is a 32-bit number. In very old operating systems like MS-DOS and Windows 95, the ISN would just start out at 0, and then it would just count up from there. So you could predict it, and this is one of the attacks that Kevin Mitnick, one of the world's most famous hackers in the 90s, used to do. He could call an administrator and say, Bozo, I just hacked your web server. The Bozo will then immediately connect to the web server with FTP or Telnet, which is what they used back then, a plain text protocol, and they will get the next initial sequence number. Now, what he can do is he can load the web page right before they make that phone call. So he can get the initial sequence number right before them, and guess what their ISN is going to be. Then they log in with FTP, so he can guess what the sequence number of their packets are, and he can, after they log in, he can send commands to the server, which will be misunderstood as having come from the real administrator. If you don't use encrypted protocols like SSH, then a bad guy can just take over your session in progress. And although that particular attack was patched back in the 90s and no modern operating system is vulnerable to it, there's another version of the same thing that works just fine on modern networks, where you steal cookies and you go into somebody else's session on a social network based on the cookie or any other network, and that works just fine. You'll be doing it in the projects. Anyway, TCP ports are an address put in the packet. This is like an apartment number at an apartment building. So mail for many different destinations comes in the same door and is sorted later by the internal address. There are 65,536 possible ports. So you can have up to 65,000 processes running on your server or your client, all receiving a different stream of data under a different port number. All right. You can block ports. That's what firewalls do. They do much more than this nowadays, but the earlier firewalls just block ports by port number, and you certainly should block ports you're not using. If you are running a server and it's just a web server running on, say, port 80 and 443, and it's not supposed to be doing anything else, you should block all the other ports. So even if somebody manages to install something else on there like Telnet or something, it won't work because the port it wants to use will be blocked. Anyway, if you blocked all the ports, you'd have no networking at all, so you have to open something. Yeah.
I remember mentioning in class that Microsoft maybe 10 or just Microsoft, all of them had 2 open ports they left open. Listening ports, and there's a way to close them off if they kept them open, they didn't care about it.
No, I don't think so. You're talking. This is a.
I may have been.
Yeah. Now, what they're asking about open ports by design. What happens is Dell servers, if you buy them, they are in fact listening on a local port, which is for remote control of the hardware, and that has turned out to be kind of a scandal. So it is a good idea to do port scans of devices and understand this. Quite a few devices are shipped to end users, and they have a remote control component that they don't tell you about. Dell servers are in this category, a lot of mobile phones, and so on. And there are always a series of scandals that come out about this. But a Windows machine, I don't think has any. If you set up a Windows machine and you turn on the firewall, it has, for example, a client machine like Windows 10, it has no open ports, not until you open them. Yeah, yeah, well, that's fine. There are other things that have that. Anyway, so 25 and 80 are open at every company because if you don't have port 25 open, you can't receive email. And if you don't have 8 or send it, well, you can't receive it at your SMTP server. And if you don't have 80 open, nobody can reach your web server to load your web page. So those are usually open. The first 1,023 ports are called well-known ports. This doesn't mean just ports that are famous. It just means they were reserved. You have to have administrative rights to listen on these ports because they are expected to have the critical services that run the internet. All the ports above that are just free for anybody to use for games and whatever else you might want to write. So there are couple dozen of these that everybody should know. And if you take any CompTIA exam like Security Plus or Net Plus, you'll be expected to know a few ports. So File Transfer Protocol is a very old protocol. It uses ports 20 and 21. 20 to negotiate and 21 to send the data, I think. Unfortunately, file transfer protocol has the ability to secure data with a name and password, but it sends the name and password unencrypted over the internet, so it is ridiculous. And all it does is make it easy for hackers to take over. So if you connect to an FTP server, your browser will ask you for a name and password, and if you foolishly put it in, it then sends it over the whole internet unencrypted, so dozens of computers get a copy of your password. So it is ridiculous, and you should never do that. Port 25 is for SMTP. That's where email is listening. There was a big scandal about Hillary's emails because she did a few things wrong. The main thing she did wrong was use her own personal server and not have a copy as required for archives of government email that she should have had. But another thing she did, which people complained about, was use unencrypted email when there are some email encryption routines available, but very few people have them set up. So in fact, you can't encrypt email if you want to send email to people in foreign countries. Many of those countries don't have the ability to receive it. And most email is currently sent unencrypted. Yeah.
So for these ports, do they apply for telecommunications?
No, we actually apply for telecommunications. No, telephones have their own protocols that are much more complicated and largely undocumented and kind of proprietary secrets to some extent. Although I think I have never found a good textbook to teach you telephone networking. I would like to take that class and teach that class. That's freaking, is hacking telephone networks, and it is very complicated. And I know voice over IP, I have been through. That's moving the telephone network onto the internet. And then I know some of the protocols that do that, but before that, there were protocols like SS7 and such that handle re-telephone calls, and they have serious defects, and hackers are hacking them all the time, and have been for decades. I don't know any book or course that will teach you those protocols. It would be cool if we had it. Anyway, good question. So port 53 is used for DNS. This turns alphabetic domain names like yahoo.com into numerical IP addresses. So you can't do hardly any networking without it unless you actually know the IP addresses of the destination, and usually nobody does. So you need to use DNS all the time. Port 69 is trivial file transfer protocol. It moves data on usually only a local area network, although it can run over the internet also. It moves data without any password at all, no authentication whatsoever. This was intended to make it easy to update the firmware and devices on a local area network. It was used in Windows 2000 to infect machines. You would turn on a Windows 2000 machine, connect it to the internet, and even if you don't open anything, no browser, no email, no nothing, it would open a TFTP server and suck down viruses from the internet and get infected. That was why they added a firewall to it after that, the Windows XP Service Pack 2. Anyway, this had an entertaining defect. The original protocol description said you will send the data, and the data will send an acknowledgement. And if there is ever an error, you will send a message about the error, and that will lead to an acknowledgement, and that will lead to an acknowledgement, and you'll have an endless bing, 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 back and forth, freezing the network. So it works until you have an error, and then it freezes up, because they didn't think of that in the original specification, and they had to fix that. That was the sorcerer's apprentice syndrome. Port 80 is used for normal unencrypted email, or normal encrypted web pages, not email. The most common protocol on the internet until maybe a year or two ago. Because of the Snowden revelations, everybody freaked out about encrypting the internet, because it revealed that the NSA had been treating American companies as adversaries and hacking them by putting listeners inside their network, like the Yahoo network. They steal the data inside the company network where it's not encrypted yet. So all the encryption that hits later doesn't matter. And this caused everyone to rapidly upgrade all their encryption as they all got very, very paranoid about the NSA, which is kind of funny because nothing you can do is locking out the NSA anyway. But this is how politics happens. You get a scandal, and that causes people to move, because if they don't keep up with the other people, then they'll appear to be the laggards. Yeah. Okay. Anyway, so port 80 is for unencrypted web pages. Port 110 was used to receive email with the old POP3 clients like Outlook and Eudora that are not that common, except Outlook Web Express is the more common version, and that goes over HTTPS. Port 119 was for network news protocol, which was popular in the days of IRC and now not used very much. 135 is remote procedure call. This is really important, used for Microsoft services that can request processes in another machine. The problem is you often have many different services running on this port, and it has been a huge security problem. 135 and 445 work together to share files and printers on Windows networks, And they have just many, many worms and virus outbreaks go through these ports because there's a lot of services and some of them have bugs. The latest one being Eternal Blue is one that the NSA developed, kept secret, and the Russians stole it and dumped it in March. And you can now take over Windows machines anywhere with Eternal Blue unless they put in their patches as of a month or two ago. Anyway, let's see if I can somehow get that to go away. All right. So, all right, that has somehow fouled up my machine, so it's ignoring me. Neat. Alt-Tab does nothing. Escape does nothing. The mouse does nothing. Well, up and down works. All right, I'll use that for a little while, and then I don't know what I'll do. Maybe I'll have to turn off my machine to end the session. Anyway, that's 135. 139 is NetBIOS, also used for file and printer sharing. 143 is IMAP4. That's, again, an email protocol, not used that much anymore. And I'll demonstrate some stuff here if I can get control of my machine. I've got control back. All right. So we're not up to where I need to take a break, so we're going to get to these Cahoots in a minute. I'm going to stop this session and start another one for the remote viewers. All right, well, there's the people. Good. I've got some people remotely attending, which is fine.